Given a reference of a node in a connected undirected graph, return a deep copy, which is a clone of the graph. Each node in the graph contains a value, which is an integer, and a list of its neighbors. So our class node is here in Java coding, and we have an integer value which is an integer, and neighbors, which is a list, which says over here that it's an adjacent list. So our test case format, for simplicity, each neighbor's value is the same as the node's index. One index, for example, the first node value equals to 1, the second node value equals to 2, and so on. The graph is represented in the test case using an adjacency list. An adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes the set of neighbors of a node in the graph. The given node will always be the first node with um, value equals to 1. You must return the copy of the given node as a reference to the cloned node graph. So this is our example 1. So we have this graph over here. This is our original graph. We should now return the same graph as it shows over here, and this is how it should be. It's a clone, and the graphs, the node and the nodes are new, and the graph looks exactly the same as this. This one, the nodes were cloned, but the graph is messed up because it's not in the same order. Doesn't have the same connections, so it's not in the same connections. And this is the list representation of the graph, and in adjacency list of the graph. And this is our adjacency list. It's empty, and the input contains an empty list. The graph consists of only the node. This one is empty. It's an empty graph, also empty. So let's move on to this. The solving it. So this is we use a DFS for this. So let's make our edge case. Edge case is if node if there are no nodes. Just in case there are no nodes, like if we don't have any nodes. So if node is none, return none. And then let's go down and make our dictionary to store our copied nodes. So dictionary this slash hash map to store our keys, which is original graph, original node, and values, which will be copied. We call it cloned nodes. We put nodes over here. So let's make our dictionary. Let's call it cloned nodes equal will be our cloned nodes will be dict. Let's put dictionary annotation, and put node as our key, and node also as our value. This will be the cloned. here this will be the original and this will be the cloned node. And now let's move on to now let's make our dictionary curly brackets data structure. So now let's make a user uh, 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 depth first search DFS to traverse the graph. So now let's define our function for function to traverse the graph. So let's call it DFS and put our node inside our as our parameter. And so if we find the node if the node is copied cloned, let's return it. So if node n is inside our cloned nodes, let's return it. Clone node equals to the value otherwise if not otherwise let's clone it. So that would be, let's make our clone variable and then assign let's make an instance of node dot value. So now let's take our clone and store it inside our clone dot cloned nodes. So we store clone inside our clone node the value of it. So there'll be node value will be clone. Store our clone node into the value of value size. Copy cloned of the dictionary key. So now let's traverse. Let's traverse the neighbor in our adjacent. Let's traverse the neighbor in the adjacent list. So traverse the neighbors in the adjacency list. So now we go to the adjacency list for the neighbor of the clone. So now let's for neighbor and so the node dot neighbors, it says over here neighbors let's add it to our clone node, the current node, and then neighbors, the neighbors are neighbors. Oops. Neighbors that append, and then let's recursively traverse. Let's call it. Let's make this recursive traverse. So that will be DFS, and then let's put this neighbor inside for each neighbor in it. Neighbor. So that's basically it. That should be it. Let's return our clone. And let's see. So let's move outside of this uh, function or method, and then return DFS node. Let's see if there's any syntax errors that need to be fixed. That should work well. Let's see if it does. Neighbors. Okay. Clone nodes is not defined there. Cloned nodes, yes. And boom, and it's been able to do it. So basically, these are our edges. So it basically copies the same exact values inside our clone. Inside our cloned nodes, and then outputs that. And our time and space complexities are time complexity. It will is O of n in the worst case if linear. Space complexity is O of n. And that's it for this problem. Let's submit it to see if it's going to pass all cases. And it's been able to pass all cases. And that's it for this problem.